This lesson is the second part of lesson 6.1. In the first lesson we learned about combinations, and today you're going to be learning about the multiplication counting principle, abbreviated MCP, and also permutations. So permutations and combinations are very similar, and at the end of this lesson you should be able to count the number of possibilities using the multiplication counting principle and permutations. So we're going to practice a few different examples of how to use both the multiplication counting principle and permutations. So remember, when we were talking about combinations, order was not important in terms of how the items were placed in the groupings that we chose. Permutations, order is important. So taking, for instance, the first three letters, if we have an A, a B, and a C, that's good for combination, even if we rewrite that as BAC or CBA, or any of those are going to be, as long as you have one A, one B, and one C, that's considered a combination. But now we're going to be looking at permutations, and we want to make sure that we're counting all of the different ways that we could put any set of letters together and any set of numbers together. So because we're looking at things that order is important, we're going to be using permutations. And we're also going to look at a case where numbers and letters cannot be repeated. So we can't have two A's or two C's, or any letters cannot be repeated, and numbers also cannot be repeated. So when we do this, we're going to have a situation where we have 7 different characters. So this that I'm setting up now is going to be what we're going to think of as the different choices that we can pick from. So the letter C here stands for character. So for the first 3 characters, we have to pick letters from our English alphabet. So because there are 26 different letters, we're going to choose from 26 to find our first letter. But because we can't repeat any of the letters, the next time we pick, we only have 25 letters to pick from because we've already chosen one of them. And then the next letter that we pick, we'll only have 24 letters to pick from. And then, after we pick our 3 letters, we have to pick our 4 numbers. And the numbers from 0 to 9 actually include 10 different digits, don't they? Because 0 is one of them. So the first number we pick, we could choose from 10 different digits. The second number we pick, we'd only be able to pick from the remaining 9. And then the third one, the remaining 8 digits, and the last one, the remaining 7 digits, because we cannot repeat any of the digits. So that's why we're having one less to choose from each time. Now, this dot that I'm putting here ends up being a symbol for multiplication, because we actually are saying that we want this digit, and we want this digit, and we want this digit. Remember, the word "and" means that we're going to multiply, and we learned that in our previous video. So when we multiply all of these numbers together, we find out the number of ways that we could get the license plate if we don't have any repeated digits, and that was 78,624,000. Okay, and that's unique license plates in the state of Michigan using the format that we have shown here, 3 letters and 4 numbers. Now we can do this problem again, but this time we are going to allow there to be repeats, because I know all of you have seen license plates that have multiple, of the same number or the same letter. So we are going to try this one with the fact that it can be repeated, but order is still going to be important. So we're going to take a look at C1, and this time when we do this, we're going to end up with a little bit higher number, because we are going to be allowed to use the same letter more than once. So when we go to pick our first character, we have 26 letters to choose from. Well, because we can repeat, we're still going to have 26 letters to choose from when we pick our second letter and when we pick our third letter. We don't have any restrictions on the repetition of the letters, so we still have the same number of letters to pick from. And the same thing goes for the numbers. We'll still have 10 numbers to choose from each time, because essentially we could have a license plate that says AAA, 1, 1, 1, 1 in this case, right? If we have allowed ourselves to pick from the large pool of both letters and numbers. So if we simplify what we have here, we would see that we have 26 to the third, and we also have 10 to the fourth. Okay, so if we look at this a little bit more carefully, when we're looking at items that can be repeated, we're taking the number of items and raising that to the power of options that we want to choose. So we're taking n total items that we have to choose from, and then we're raising it to the power of items that we have to put into our formula. So again, 10 to the fourth would be represented by n to the r. And that's when things can be repeated. So you'll have some more opportunities to practice this. I know the first time you see it often is challenging to understand, but we'll keep working on this. So if I multiply all of these together, you'll notice that there are 175,760,000 unique license plates before they have to decide, okay, we need to find a different formula for creating license plates, because there may be this many license plates created and needed in the state. So look at the difference between this number, where we had 78 million, and now, because we can repeat the digits, we have about 3 times as many, a little bit more than 3 times as many options, because we are allowed to, choose the same letter or number more than one time. Okay, so you're going to want to copy this information into your notes, the difference between the multiplication counting principle and permutations. So MCP is a method to count the number of possibilities by determining the number of choices in each category and multiplying them together. And that's what we used when we were looking at the different license plate possibilities. I would like to point out, though, if the problem has no repeats and order doesn't matter, you're going to use combinations like we had in our previous video, in our previous lesson. So one of the things that you're really going to need to pay attention to is if order is an important factor in the problem that you're looking at. And we will continue to talk about this because it's the main idea, the main difference between permutations and combinations. So when we were looking at the license plate problem, order did matter, because you can't just throw some letters up there and not worry about the order. The order is very important, because ABC and BCA are 2 different order combinations or letter combinations. One last thing that I would like you to add into this box: if the problem does have repeats and order does matter, then multiply the number of possibilities in each category by using the multiplication counting principle or permutations. So you may want to review the last example that we just did with the license plate, or just wait, you'll see another example of this in the same video. Now, the definition of permutations is the number of R item arrangements that can be formed from a larger group containing n items. So just as a note here, we cannot use this notation for permutations, okay? That's only for combinations. So I would like to put here the way that you're going to write the permutation notation. It's going to still be similar to our combination notation, but this time we're going to have the letter P here instead of the letter C. And this just means that we're going to take the number of items total, factorial, over the difference between the items that we're choosing from the big group. Okay, so this is our formula for permutations. So we're going to try this out in the next couple of examples. So is order important when we're looking at permutations? Absolutely, yes it is. Can you repeat items? No. All right, so let's go back to what we were talking about in the multiplication counting principle. When order does matter and we have repeats, we want to be using the multiplication counting principle. All right, there are 4 problems in example 2. We want to write in words how to read each permutation or factorial, and then find the value of it using the appropriate formula. So as you see, I've marked example 2A as one that you need to do on your own, as same as part D. And then I'm going to do part B and part C for you so that you can get the idea. So how do we read this? For part B, it's going to be the permutations of 4 from 10. And if you're looking at the way that this is notated, you can see that N is 10 and R is 4. R, remember, is the number of items that we're pulling out of the group of 10 to arrange. And remember, order is important, so we're taking 4 items from 10, but we cannot have them in any, no, it's not just choosing 4 and then saying, hey, we have those 4. They have to be in a specific order, going from left to right or up to down or whatever situation it is. But we also can write this out in a factorial form, and remember the formula that we have is going to say n factorial over n minus r factorial. And if we write this out completely, I would have 10 times 9 times 8 times 7, as you know, over, and 10 minus 4 is 6, so I'm just going to have 6 times 5, and keep going all the way down to 1. All right, so what are the things we can cancel? Well, we can cancel anything from 6 on down. Okay, and we're just left with this. And if we put that into our calculator, you'll see that we get 5,040 as an answer there. So when we have permutations of 4 from 10, that's the total of 5,040 different permutations. All right, how about part C? Part C says 12 permutations 0, which that actually means permutations of 0 from 12. Again, here n is 12 and r is 0. So if I write this out in the formula form, that's going to be equal to 12 factorial over 12 factorial, and anything over itself is just 1. So there's only one way to choose 0 items from 12. All right, so please finish up with problem A and problem D, and then we're going to go on to the next example. In example number 3, it says how many different arrangements can be made for the following books to be placed next to each other on a shelf when only 5 books will fit on that shelf. I want to point out that the word arrangements really does indicate that we want to use permutations. Whenever you see the word arrangements, that's going to indicate or kind of give you a clue that permutations are going to be needed. So every problem probably won't have the word arrangements, but in this case we can see that it does. Only 5 books are going to fit. Well, how many books do we have? There's a Latin book, a French book, history, geography, math, physics, and chemistry. So we have a total of 7 books, but we can only choose 5. We only have 1 of each type of book, so we can't have any repeats. So that's a good thing to note. So there's not going to be any repetition. And we know that order does matter. So these two things right here lend itself to using permutations. So in order to try this out using the multiplication counting principle, I've set up 5 slots. Remember, we're only picking 5. That's the amount of space that we have to put on our bookshelf. We can only use 5 of the 7, and there is nothing that says that we have 2 Latin books, 2 French books, anything like that, so we're not repeating anything either. So in our first slot, we have 7 different books to choose from. So we have 7 choices. But once we choose one of them, we now are down to only 6 choices, and after we choose those 2, we're down to just 5 choices left to pick from the books, and then 4, and then 3. And remember, we're multiplying these numbers together because we're choosing this book and we're choosing this book, and we're choosing this book, etc. So let's go ahead and multiply those together, and we get 2,520 ways to arrange the book. And if we do this with permutations, we would write it like this: 7 books, and we're choosing 5 of them. And if we write it out in notation, well, not notation, but in formula form, we'd be writing 7 minus 5 factorial, and that's on the denominator, and that would end up being 7 factorial over 2 factorial. And if I write this out over just 2 times 1, and we could cancel those. Now, if you notice, this is exactly the same thing as we had when we were using the multiplication counting principle. So we still have 2,520 ways to arrange these 5 books on our shelf out of the 7 that we started with. So there are 2,520 permutations, just like there were 2,520 ways if we use the MCP. In example number 4, you're asked to find the different number of passcodes there are for an iPhone. So if you're putting in an iPhone password and there are 4 digits, remember the only digits that you can use are 0 through 9. I'd like you to figure this out on your own. So what would happen if you can repeat the digits? So for instance, you choose 4777, or what if you cannot repeat? Okay, so you're doing a comparison between yes, you can repeat the 4 digits, or no, you cannot repeat. So again, go back to one of the previous examples that I gave so that you can look at using the digits 0 through 9. And I would like you to see if you can find the solution to both of those on your own, please. For example 5, we're being asked to find the different ways that an announcer for a basketball team can introduce the starting 5 players. Well, remember, when we're introducing people, we're not going to repeat any of the people, and order is going to be important because there's only 5 slots to fill, and we don't want to just say all of them at the same time. So we have a very specific order that we want to do. So no repeating, and order is important. So of course here we're going to be able to use permutations, and we could also use the multiplication counting principle. So when no repeats and order matters, we can use either of those. So there's player 1, player 2, player 3, player 4, and player 5. So when we have 5 players and we want to introduce them, we have to choose them in a very specific way. So from when we pick the first player, we have 5 to pick from, and then the second time we pick a player, we only have 4 to pick from. And as you go, you reduce the number of people that you have to choose from by 1. So if I do this, this is 5 factorial, and 5 factorial is 120 different ways, different orders that I could introduce those players, and that's just using the multiplication counting principle. If I did this with permutations, I would have 5 players to pick from, but I'm also picking 5. So I would see this as 5 factorial over 5 minus 5 factorial, and from a previous lesson, 0 factorial is just 1, and 120 is going to be the numerator. So that just means that we have 120 different ways again. So this is just comparing the multiplication counting principle to permutations, and again we see that the result is the exact same. So no repeating and order matters, you use permutations. Okay, we have 2 more examples left. Both of these I would like you to do on your own, but I do have some hints for you. In example number 6, it says how many different 5-digit passwords are possible if you can only use 0 through 9 numbers and numbers can't be repeated. Okay, so no repetition And order is important because when we're putting in a password, remember if you don't put in the password the correct way, then obviously you don't get in to whatever you're trying to get into. So order does matter when you're entering a password. So here you could use permutations, or you could use the multiplication counting principle because no numbers can be repeated. So you're going to choose whichever one you like and solve that on your own. Some people will find that it's easier to use the permutations. And then down here, because numbers can be repeated, you need to use the multiplication counting principle, and that goes back to the very first example that we started with. So I would like you to do this on your own as well. Okay, so just a reminder that we have slot 1, slot 2, slot 3, slot 4, and slot 5 when we're going to enter in the 5 digits, and then these are the only digits that you can choose from, 0 through 9. And just a reminder, there are 10 numbers in that set. All right, and then for example 7, the CLHS varsity girls volleyball team is selecting 2 team captains. 2. And how many different captain pairs can they have if there are 12 girls on the team? So just a hint, N is going to equal 12 and R is going to equal 2. Now, what's up to you is how are you going to choose this? Is it going to be using combinations where order does not matter, or permutations where order does matter? Okay, so that's something to consider. Is order important when you're choosing 2 team captains from a group of 12 people on the team? So this is another one where I'd like you to choose on your own. Maybe you can talk to some people nearby and figure out, is it going to be combinations? Does it matter which order we pick these 2 people? Or is it going to be permutations? And that's really the deciding factor here. Because the 2 formulas are different from each other and you're going to get a very different number depending on which one you choose. Please pick the correct one. And I will answer questions when we have our assignment on this particular lesson.